Hi, so I'm Christopher. I'm going to talk about stream processing with Meta Ocaml. So I work at Ahrefs. One of the things we're building there is a general purpose web search engine. And one of the key components of the query pipeline in a search engine is basically a stream processing pipeline, stream processing problem. So I'm going to talk about how we can use like some Meta Ocaml to solve that. There will also be some C++, so avert your eyes if you feel the need to. So in a search engine, we have an inverted index, which maps from terms to the list of documents that contain those terms. We also have other features like how many times does this term appear in the title of a web page, or how many times does it appear in the content of a web page. So if we imagine our query is functional programming, we have functional, all the documents that have functional in it, programming, all the documents that have programming in it, other things like scores for that term document pair. And we want to end up with a list of all of the documents that, in a simple case, just have both functional and programming. But we can get more complicated streams as well. So maybe F1 is the number of times it appears in the content, F2 is the title, and we want to say, okay, I want to have F1 and F2, them merged together, and maybe I need to have some criteria. It has to appear in the content twice and the title once or something. Then we join that with score, then we join that with the document IDs for each term, and then we join those terms together. So it's a relatively complicated DSL. We can get much more complex than this, and our backend is written in C++, where describing something like this is somewhat painful. So we want a better way to do it. There's this cool library called Strymonas. It's described in this paper and some earlier papers, and it allows you to describe a stream processing pipeline in Ocaml, and then it will generate code using Meta Ocaml. It can generate Ocaml code. It can also generate, it has a C backend to generate C code. And it promises that the generated code will have complete fusion. So if you don't have in any individual step, if you have no function calls or allocations, your final result will have no function calls or allocations, and it will be as fast as you could do a handwritten state machine. So just a quick example from the paper. You have these operators, and you can compose the operators together. So maybe you have a stream of integers starting from 1, and you're going to say I want to multiply every integer by itself, and then I'll have maybe ex2 is another block I want to build with, and so now I want to say okay, mod every integer and keep only the ones where the result is greater than, or mod every integer by 17 and keep only the ones where the result is greater than 7. Then take 10 of them and sum them up. So on the left, that's pretty easy to understand what's happening there. And then on the right is the generated code in Ocaml, and it's very imperative. It's not super easy to understand, but that's okay because we really only have to look at the stuff on the left. So if we go back to the example I was showing for our intersect algorithm, these are some of the operators that we can use to build up our pipeline. So emit terms is kind of the final step that we will call. And we're going to tell the library we have this function emit that's defined elsewhere in C or C++, and we're just telling it how to take the inputs to this operator and pass them into that function and call it. And then the iter bit at the end is what actually iterates through the pipeline. Then maybe we have this other block called intersect term that is again made up of other blocks where we're going to create streams of scores, and maybe we'll apply weights to scores because we care about functional is more important in the query than programming, for instance, and same thing with the other features, and we'll apply some thresholds to them and combine them together, then drop everything we don't care about. Then for those two terms, we're going to merge them together and emit them. And we could even have more things at the end, like I want to merge the terms together and then only keep the results where I have, if my query is 6 terms long, 3 of the 6 terms present. And then we will emit them. And of course, since this is just Ocaml code, you could even take intersect 2, which is for 2 terms, and use some fold operations and more easily generalize that to intersect of 15 terms. So I won't show all of the generated C code because it's quite long and not really human readable by design. But on the right, you can kind of notice this block contains more or less all of the logic that we wanted to encode in our pipeline, all in one place. And then we're going to assemble everything together and emit it. And in our original pipeline, we're applying the scores, we're applying by some weight, and then we have some other mathematical operations. But if we look at the final result, we only end up doing those calculations when we actually want to emit. So we're not wasting CPU cycles doing mathematical operations on documents that we don't care about. And then so the last bit is we can integrate this into a C++ program where we can set up some test data. We have the emit function that we that we told the library about, and then we just call the intersect2 function that it generated for us.
Done?
Yep.
Oh, good.